Hi! In Crash Course Physics episode 9, work, energy and power are the main actors, especially conservation of energy. And this is, if anything, the central pillar of physics, that energy is always conserved no matter what kind of system we're talking about. It usually starts with mechanical systems, as shown here, but the principle actually goes much deeper. Now, it seems a bit odd that we would want to multiply a force with a displacement. If we move some object with a certain force, we've learned that force times time gives us the change in momentum. But why would we want to multiply force with displacement? Well, it is because of a little algebraic manipulation that the force times a little space interval dx is actually force times velocity times dt. But you recognize force times time is actually the change in momentum v dp. That is, there is some sort of fourfold relationship between force, displacement, velocity and momentum. And this relationship has a geometric interpretation. If we plot force versus displacement, or versus position, and velocity versus momentum, then there's a geometric relationship between these two areas, because as we displace our object, force times displacement dx, so this little rectangle that gets added on the left, has the same area as velocity times change in momentum dp, that is the little trapezoid on the right. That is, no matter how the object gets displaced, both areas change in the same manner, that is, they can be said to be equal. And this equality, or this area, is called the work. The work imparted on the object translates to its kinetic energy. The kinetic energy, of course, since this is a linear relationship, is momentum times velocity over 2, area of a triangle, which gives us this formula m over 2 times v squared. Now, the relationship is much more general because it doesn't have to assume that force is constant. We could have applied more force or less force while the object is sliding over the terrain, or maybe this is a force field, so that has a certain value at each different position in space. In this case, the area, the work, is the integral of the force over position. Now, this gives rise to the notion of energy when we think of the work performed on the system as being drained from some energy source outside of it. So the potential energy is the work that can still be performed on the system. So we imagine that we have a certain amount of energy E0 outside, and then we transfer part of it onto the system. What's left, E0 minus W, is the work that we can still perform in the future. In this case, the potential energy plus the kinetic energy is a constant. This constant of energy is actually an arbitrary set origin for our energy scale. And the potential energy is usually the function of the position. In the simplest case, when we drop an object in the gravitational field, at the beginning it has lots of potential energy because its high position allows us to accelerate it a lot, but it has a low kinetic energy, 0 if we just drop the object. As the object is falling down, potential energy is converted into kinetic energy as the object picks up speed. Yet another way of thinking of this is in terms of potential. The high position of the object relative to Earth's surface can be thought of as a gravitational potential, usually denoted with the uppercase letter phi, which is the gravitational constant g, the Earth's gravitational constant, not the uppercase g, times the height. And this potential gets multiplied with the mass. The more mass we have at this high potential, the more potential energy we have at our disposal. At the same time, momentum p can also be thought of as sort of a quantity that is at the low potential, at the low velocity, 0 for example, and as the object falls down, the mass goes down to a lower gravitational potential, maybe down to the ground, while the momentum acquires a higher potential, and the corresponding potential of momentum would be velocity. Now, of course, this momentum comes from outside. So this at the beginning is not the momentum of the object, but it is in the Earth, and then the Earth imparts this momentum, transfers it onto the object. The work that has been shifted from one potential to the other is mgh, since it is a gravitational potential, but also it equals mv squared over 2 because it is the energy associated with the kinetic change. This equation actually gives us this formula on the upper right corner, that v equals square root of 2gh. Finally, here's a little simulation of what a pendulum looks like. A pendulum also constantly transfers potential energy into kinetic energy until one reservoir is drained, and then vice versa. So at this highest point, there's lots of potential energy and no kinetic energy, no velocity. And at the lowest point of the pendulum, we have just kinetic energy and no potential energy. So I hope you enjoyed these nitpicks for this episode of Crash Course Physics. Don't forget to subscribe and follow me on Twitter.